Hello, and today we're going to continue looking at De Morgan's laws. So at the end of last lesson, we were looking at what is the opposite of A or B, the negation of A or B. So at the end of last lesson, we said that the not A or B is not A and not B. So we'll continue on with example 7 over the page. So it says here, from the set of numbers 1, 2, 3 up to 9, the set of numbers that are either even or prime is 2, 3, 4, 5, 6, 7, 8. So the numbers which are even or they're prime. 7s are prime but not even. 8's even but not prime. So part A is saying, select the numbers that are neither even nor prime. So we're looking for numbers which are not even and not prime. The only two numbers which are not even and not prime from our set is 1 and 9. So neither even nor prime is the set of 1 and 9 because 1 is not even and it is not prime, and 9 is also not even and it is not prime. Part B, find another way that this set of numbers could be described. So it's applying De Morgan's laws using words. So we're starting off with neither even nor prime. That's the same as saying not even and not prime. And that's the same as saying odd and not prime, because not even is odd. Odd and not prime. Therefore, the set of numbers are odd and not prime. The set of numbers that are odd and not prime. So there's also another one of De Morgan's laws. So last time we negated A or B. Now we're going to negate A and B. So first consider the statement that A, John is 2 meters tall, and B, John weighs at least 200 kilograms. The statement A and B says John is 2 meters tall and weighs at least 200 kgs. The opposite statement, A and B, noting A and B, is John is not 2 meters tall, because it's the opposite of A, or he weighs less than, the opposite of at least 200 kilograms. He weighs less than 200 kilograms. So in general, not A and B is not A or not B. Again, we'll use a set of numbers 1 to 9 to demonstrate this. So 1, 2, 3, 4, 5, 6, 7, 8, 9. Find the set of numbers that are even and prime. So it's only 2. So part A, find the numbers that are not even and prime. So anything but 2. So not even and prime is the set of numbers everything but 2, because 2 is the only number that's even and prime. So if 1, 3, 4, 5, 6, 7, 8, and 9, close squiggly brackets. B, what is another way of saying this? So in words, not even and prime means not even and, or opposite of and is or, not even or not prime. And not even means odd, so it's odd or not prime. And that agrees with our set of numbers. It's the numbers that are odd, 1, 3, 5, 7, 9, and not prime, 4, 6, and 8. So therefore, the set of numbers that are odd or not prime. Example 9. Negate, so say the opposite of the following statements. Part A is divisible by 2 or N is divisible by 3. So we need to negate A or B, which is not A and not B. So noting A is N is not divisible by 2, the opposite of or is and. So and the opposite of n is divisible by 3 is n is not divisible by 3. N is not divisible by 3. In other words, n is divisible by neither 2 or 3, because it can't be divided by 2 and it can't be divided by 3. For part B, we've got statement A and statement B. The opposite of A and B is not A or not B. So the opposite of bigger than is less than and equal to. Flip the sign and also add an equal sign. We need oppositing and, which is or. The opposite of less than and equal to is bigger than. So or x is bigger than 5. So the opposite of x is bigger than 0 and x is less than or equal to 5 is x is less than or equal to 0 or x is bigger than 5. So they're the two De Morgan's laws, the negation of A and B and A or B. Just remember, opposite of and is or and opposite of or is and. Now we're going to introduce a few more terminology and symbols. So a proposition that includes variables is known as a propositional function. So for example, x is bigger than 7. It's got a variable x and it's got a statement bigger than 7. Another terminology, quantifiers, are used to give information about the values of variables in these propositional functions. So specifically, we've got a universal quantifier, which says for or, and it's written with this fancy symbol which looks like an upside down A, literally. Write an A upside down. That's the for or symbols. It means that all possible values of the variable are considered, everything. So example 10, I'll write the following propositions in words and determine if it's true or false. So for part A, for all x, so upside down A means for all x in the reals, the x is bigger than 7. So writing this in words, for all, that's the upside down A, real numbers x, real numbers x, we have the condition that x is bigger than 7. Now, is this statement true or false? It's false because there are real numbers which is not bigger than 7. So since 1 is a real number and 1 is not bigger than 7, so proposition is false. Part B, how do we read that statement? Well, for all, upside down A, for all x in reals, we have the statement that x squared is always bigger than and equal to 0. So in words, for all real numbers x, x squared is always bigger than or equal to 0. Is this true? Yeah, if you square any number, it is positive. If you square a positive number, it's positive. If you square a negative number, it's positive. So regardless, whatever you square, it's always true. So if x is positive or 0, then for sure x squared is positive or 0. If x was a negative number, then you know that negative times negative is positive. So x squared is also a positive number. So therefore, proposition is true, because regardless of any x value you choose to have, the statement x squared is bigger than or equal to 0 is always holding true. So proposition is true. Another funky symbol that we have is the existential quantifier. There exists. There exists. It is a backwards E. There exists. It means that there is a value, not necessarily every value, but there is a value which makes the statement. So example 11, let's look at these mathematical statements and write them in words and see if they're true or false. So for part A, backwards e, so there exists x, which is a real number, so there exist real numbers such that that real number is bigger than 7. So in words, there exists a real number x such that x is bigger than 7. So backwards e, there exists a real number x such that x is bigger than 7. So is this true or false? Or it's true. Can you find me a real number which is bigger than 7? Because there exists is just finding one such value. For all means it has to be true for everything. So if we can find one such real number which is bigger than 7, then we're good. Well, yes, we can. So consider 8, which is a real number. 8 is bigger than 7. That's a true statement. So therefore, proposition is true. Part B, there exists, so backwards E, there exists a natural number, n for natural number, such that 2x plus 1 is a multiple of 3. So in words, there exists a natural number x such that 2x plus 1 is a multiple of 3. So when you write exist statements, you can see that it always pairs up with such that. So there exists blah, 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 such that blah, blah, blah happens. Is this statement true? So can you find for me a natural number such that 2 lots of that natural number plus 1 is a multiple of 3? Yes, 1 is a natural number, 2 times 1 is 2, plus 1 is 3, which is a multiple of 3, so we're good. So consider x, which is 1, that's a natural number, 1 is a natural number, so 2x plus 1 is 2 times 1 plus 1, which is 3, which is a multiple of 3. So therefore, proposition is true. So the difference between for all and there exist, for all has to be for every possible value of interest. There exist is, as long as you can find me one, then you're good, then we are happy. Now we're combining the negation, the opposite, with these for all and there exists. So consider the statement, the false statement, all prime numbers are odd. I mean, you know that's not true because 2 is a prime number and that's not odd. We can rewrite this as for all prime numbers p is odd because all prime numbers are odd. That's what the statement's saying. The opposite of this false statement is a true statement, right? That there is a prime number, p, where p is not odd. And we know that's true because 2 is that existing number. So the opposite, the negation of for all values is a there exist. So the opposite of for all is there exist a value, x, in our domain of interest, big X, where not p, remember that little sideways L means not of that statement. So in other words, all it's really saying is there exists x and x in your domain of interest such that the not p statement is satisfied. And similarly, the opposite of there exist is for all. So opposite of existing is for every value in your domain of interest, the opposite statement happens. So for all values x in your domain of interest, you're interested in not the statement. We can combine for all and there exists as well, and in fact we can combine both for alls. So suppose we have a for all x in reals and for all y in reals. It just means everything is in reals. So we can just write that as a simple for all x and y in reals. So we can simplify our notation. So we read this as for all x and y in your real value domain. We have a note here that order matters. If we consider the statement for all x there exists a y such that blah 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 happens, means that for every value of x there is one y value which you can find to make the statement true. In contrast, if we say there exists x for all y, means that you can find an x value that makes the statement true for every possible y value that you can consider. At the moment it sounds confusing, but if we do example 12 over the page, then hopefully it makes a bit more sense. So over the page to example 12. For each of the propositions below, write it in words and tell me, is it true or false? So let's look from statement A. We start off with for all x in your reals, there is y in the reals such that the statement y is bigger than x squared holds. So let's read it again. For all x values in reals, there exists a y value in reals such that y is bigger than or equal to, y is bigger than x squared. So in words, for all real numbers x, there exists a real number y such that y is bigger than x squared. Oh hey, now Kevin's joined us. Hey Kevin, and you can all hear Kevin saying hi as well. I'm recording Kevin. Hey, I don't know, maybe Arla can catch Kevin up. Okay. So that statement was, for all real numbers x, there exists a real number y such that y is bigger than x squared. So you're thinking, for any real number of your choice, can I find you a real number y such that y is always bigger than x squared? Yes, you can, because there's infinitely many real numbers. So regardless of whatever x number you give me, I can always find a bigger number that's bigger than the square of your number. So yes, this is true. So proposition is true since there are infinitely many real numbers. So we'll look at B first and then we'll compare the difference between the two. So part B, if you read left to right, we're starting off with there exists a real value such that for all real values y, the statement y is bigger than x squared. So in words, there exists a real number x such that, so see how there exists and such that pairs together, such that for all real numbers y, the statement y is bigger than x squared. So can you find a real number such that for any real number you throw at me, y is bigger than x squared? No, because if you consider any real number, you can always find a number which is not bigger than that. So consider y is -1. So if y is -1, can you find an x value such that -1 is bigger than x squared? No, because squaring anything is always positive, is always bigger than or equal to 0. So it's false. So if you let y be -1, then there does not exist an x in the reals such that -1 is bigger than x squared. So therefore proposition is false. have a think about the difference between A and B. It looks similar, but it's not. A is saying for any real number that you give me, I can find you a number y such that y is bigger than x squared. Which is true, because I can always one-up you with whatever number you give me, because there's infinitely many numbers. In contrast, B is saying there exists a number that for anything you give me, you are always bigger than me, which is not true, because if y was -1, then you can't. Whatever you square can't be bigger than -1. And the last thing to finish off is, down here, 2 notes. If you want to show that there exists statement is true, all you need is one sample to make it work. On the other hand, if you're wanting to show that for all statements is false, then you just need to give me a counterexample. We will talk about a bit more about proving by counterexamples later on in the term when we come back. And I think we'll call it a day there. To-do list, relevant to-do list is in green down here. Exercise 4.2, page 157, question 9, B, C, E, F, question 10, A, C, D, F, and question 11, 12, 13 optional if you have nothing better to do, and 14. That's it.